Imagine trying to buy a sack of maize at Owino Market, but the seller just guesses the weight by lifting it in his arms. You would never know if you were getting a fair deal. Now imagine that same guesswork being used to build the massive Ginger Bridge. If the engineers guessed the length of the suspension cables, the results would be disastrous. That is why we rely on exact measurements. They give us a reliable, shared language that turns a chaotic world into something we can understand and build upon safely. Without a standard system to measure, trade falls apart and construction becomes dangerous. We need these numbers to understand how the physical world actually works. Look at this sack of matoke on a scale. To know how much physical stuff is inside, we measure its mass in kilograms. As this jerry can fills with water, we measure its volume, how much space an object takes up. Measuring the volume of water in a flat-sided container is easy enough. But look at this piece of rough granite from the Ruwenzori Mountains. It has bumps and jagged edges that make it impossible to measure with a simple ruler. We can easily find its mass on a scale, but to find the volume of an oddly shaped object like this, we rely on a specific scientific method that uses water to do the work for us. This is a measuring cylinder, and it is the perfect tool for solving our irregular shape problem. We mark the starting water at 30 cubic centimeters. Lowering the granite pushes water out of its way, making it rise to 50. The stone displaces its exact size in water, so we subtract. 50 minus 30 leaves exactly 20 cubic centimeters. By letting the water show us the displacement, we can find the volume of any solid without needing complex geometry. But having a precise tool is only half the process. The person reading that tool can still introduce mistakes if they aren't careful. Look closely at water in a narrow tube. The surface forms a curved dip called the meniscus. Looking from above or below distorts it, creating a parallax error. To get the true measurement, your eye must be perfectly level with the curve's bottom edge. Even then, researchers take several readings and calculate the average. This helps minimize the impact of any single random mistake. Reliable science requires both the right physical tools and disciplined, careful observation. When we combine mass and volume, we arrive at a single number explaining an object's behavior, its density, found by dividing mass by volume. As seen in these boxes, it doesn't tell us overall weight, but how tightly packed the matter is inside. We often assume that heavy things will sink in water, while light things will float. But weight alone doesn't actually determine what happens. Density is the actual rule here. If an object is denser than the water beneath it, it will sink. If its density is lower than the water, it will float. To see this in action, let's look out over Lake Victoria. Here we have a massive wooden boat resting on the surface and a small iron nail held just above the water. The wooden boat weighs tons, but its mass, along with all the empty air inside the hull, is spread out over a huge volume. Because it is so spread out, the boat's overall density is lower than the water, which is why it stays afloat. But watch what happens when we drop the small nail into the lake. It cuts through the surface and plunges to the bottom. The nail is light, but every bit of its iron matter is packed into a very small amount of space. That makes it denser than the water it displaces, and gravity pulls it down. From tailoring clothes to understanding massive ocean currents, these measurements decode the forces shaping our world. Accurate measurement is the heartbeat of science and everyday life.